In this demonstration, you will learn how to evaluate the performance of a centrifugal pump with a volute using ANSYS Fluent. In this example, I've already loaded the mesh of the centrifugal pump and volute into Fluent. Since the impeller and volute cell zones are in different frames of reference, I must specify a mesh interface. This meshing interface allows ANSYS Fluent to solve the flow equations across the interface in between the adjacent fluid zones. Next, I want to set up my turbulence model. In this case, turbulent fluid interactions will be described by the K-omega SST model, which effectively predicts flow separation in turbomachinery, allowing for accurate evaluation of a pump's performance. The working fluid in this case is water, which I must add to the list of loaded materials before changing the fluid in each cell zone. Water will be flowing through the impeller cell zone. The impeller will be rotating about the z-axis. To describe this, I will check the frame motion option. In this case, the correct rotation axis is set by default. I must now define the impeller's rotational speed, which is 1450 rpm. The volute fluid zone is stationary in the absolute reference frame, so I only need to change the working fluid to water. Now I can remove air from the fluid list since it's no longer present in any of the cell zones. With the cell zones appropriately defined, I can start editing some of the boundary conditions. The impeller hub moves with the impeller fluid zone. To describe this, I will set this wall boundary as a no-slip rotating wall with a velocity of 0 relative to the impeller fluid zone. The same settings apply to the impeller shroud. The in-block shroud wall is stationary relative to the absolute reference frame. Therefore, I will describe it as a rotating, no-slip wall with a velocity of 0 in the absolute reference frame. The inlet was automatically set as a pressure inlet with a gauge total pressure of 0. The volute's outlet is set as a mass flow outlet. The fluid will be flowing out of this boundary at a mass flow rate of 77.5 kilograms per second in a direction normal to the outlet's plane. With my boundary conditions defined, I can define the solution method, solver controls, and output variables. The solver will use a coupled scheme with a node-based gradient. The run will be pseudo-transient with high-order term relaxation. To improve the stability of the solution for turbulence equations, I will reduce the turbulence kinetic energy and scalar dissipation rate relaxation factors to 0.5. Now I will set the output variables. I am most concerned with the head produced by the pump. To set the head expression as an output variable, I must first define the mass-weighted average outlet total pressure variable and the mass-weighted average inlet total pressure variable. Now I can define the head expression using the Fluent expression calculator. All I need to do is take the difference between the mass average total pressure at the outlet and the inlet and divide that difference by the density of water multiplied by the acceleration of the fluid due to gravity. Finally, I will have the head value printed to the console after each solver iteration. The convergence of this solution is best monitored by locally scaled equation residuals. For this run, the solver will use a timescale factor of 5. Using these settings, the solution should converge after 300 iterations. Now I can submit the case to the solver. After 300 iterations, the head has converged to a steady positive value. I will compute its exact value. That seems reasonable. Prior to this portion of the demonstration, I prepared a couple of scenes that describe the calculated flow field. Here is a plot of the velocity vector flow field surrounded by the impeller and volute wall boundaries. Here's a contour map describing the static pressure at the same location. Finally, shown is a velocity contour describing the flow uniformity at the volute outlet. This concludes this demonstration, showing you how to simulate and analyze the performance of a pump with a volute using ANSYS Fluent.